Hello class, this is your instructor Dr. Mayes. We are in chapter 17 of the dynamics. This is the last section of chapter 17 which deals with equation of motion, general plane motions. In previous section we studied the rotation about a fixed axis, the translation, and we also introduced you to the concept of moment of inertia. Today is a continuation, and with this topic, which is 17.5, we'll conclude the chapter. So what you will learn is to analyze objects or rigid bodies undergoing general plane motion, both translation and rotation. In a similar approach that we learned previously, we'll introduce you to the concepts and some examples. The reading quiz, the first one: if a disk rolls on a rough surface without slipping, the acceleration of the center of gravity, g, will be equal to the angular acceleration multiplied by r, and will be the friction less than mu s n. So the answer is C. The second reading quiz is: if a rigid body experiences general plane motion, the sum of the moment of external forces acting on the body about any point P is equal to IP alpha, or the moment of inertia about that P multiplied by the angular acceleration for 2D planar motion. Another application is this compactor vehicle, or the soil compactor vehicle, which accelerates forward. We know that the front wheel, which is given in this schematic, or the free body diagram, is experiencing a general plane motion because it's moving horizontally, as well as the wheel itself is rotating. So that's described a general plane motion. Now the question could be, could you compute the forces acting on the roller shaft, which is attached to the center of that wheel at G, and we designate these reaction forces by the component, of course, the Gy and Gx. Definitely when we analyze systems like that, we must first draw the free body diagram and the kinetic diagram. The kinetic diagram typically follows your preferred Cartesian coordinate system or preferred normal and tangential. Whatever Cartesian or whatever coordinate system you're using, you must follow the right hand rule as well as follow the positive direction. I personally, what I use is attach the coordinate system along the inertias. For example, I would deal with MAG to the left to be the positive, if in this case, and in this case also I use the counterclockwise to refer that the moment is positive along that direction, where I dedicate that IG alpha is counterclockwise and is positive direction. Now looking back to the free body diagram of that compactor wheel or compactor cylinder, we have a normal force attached at the contact, and it's normal to the surface, as well as we have a frictional force. Now because the wheel is moving to the left as a result of counterclockwise rotation, which result into accelerating the center of gravity of this vehicle to the left, MAG, then there probably could be different kinds of friction forces. It could be a push friction force or a slipping friction force, or it could be a static, not moving. So in any ways, we designate a friction force vector and we decide a location or an orientation. In this case, we choose to have to the right. Another application example is this roller, which is being pushed forward with a force with a magnitude of 200 Newton at an angle of 45 degrees. A question could be, determine the translational acceleration, which is the acceleration of point G to the left, AG, as well as the angular acceleration of the wheel or of the roller itself. Could also have questions related to the frictional force at A or the reaction forces at G and A. Another example is the dummy used in testing vehicles for safety purposes. This dummy, just before the impact, the entire vehicle will experience a deceleration due to the vehicle is becoming to a full stop as a result of the impact. So we would know how much is the deceleration. Now, because the vehicle or the dummy is sitting on a seat and belted, we could analyze the motion of this dummy by using its center of gravity, where this center of gravity, using a normal and tangential analysis, will seem to be rotating about a point, let's say A. So we would know that, let's say if you have a camera, you will see this rotation of that point G. Now, as an engineer, most of the questions will relate to design a proper seat belt. And to do that, you must calculate the reaction force between the dummy and the seat belt, which means know how much is of that force transmitted to the belt. Okay. Alright, let's dive into the theory. The theory of the general plane motion is not that different from what we discussed previously, except that the general plane motion will involve both rotation and translation. Let's consider this object that has forces acting on it and free moments, m's, and its own weight. The kinetic of this same object can be described by labeling first the inertia, the angular inertia, which is Ig alpha, where we are describing everything with respect to the center of gravity, and also the translation, which has a vector component of MAG, and that could be decomposed along the x and y into two vectors, MAGY and MAGX. That's if we are using Cartesian. So both of them should be equivalent using the equation of motion, which is summation of forces in the x direction. All the components of these forces must be equal to the linear inertia along the x, MAGX. as well as the forces in the y direction must be equal to the magy, and the moments of all these forces and the free moments, taking into account that we choose a proper orientation for the positives, and commonly we use counterclockwise for 2D plane motion. And we calculate the summation of all the moments about that g to be equal to ig alpha, which is the rotation. Now, possibly you could choose different point than g, let's say a p. Then this, we compute the replacement of that if you choose different point for simplicity or for elimination of some of the unknowns. You could use different point, as we will see in some example today. You could choose a different point, such as point P, but you have to calculate or recalculate the moments, which is the left-hand side, of all these forces and moments about the point P, and calculate this equivalent inertia, which has to be in addition to the, or is equal to the IG alpha and the moment of MAG, which is a cross product between the vector MAG with, or R of G with respect to P cross MAG. And that can be decomposed in scalar form. One typical example of general plane motion is the rolling problem or the frictional rolling problem. When analyzing the rolling motion of a wheel or a cylinder or a disc, such as in this problem, which is driven by an external force, say P, with a known direction and magnitude, what we want to know whether this body is slipping or rolling without slipping. And to do that, we must apply equation of motion and investigate the case. Let's consider this example and dive into the equation of motion. First of all, the equation of motion is obtained from free body diagram of this wheel. The forces of this wheel include the external force P, the weight of this wheel applied on G and it's going downward, a reaction force upward. This wheel is being pulled to the right, which causing this wheel to rotate clockwise. And if we take that motion, then we can say that there exists a friction force F, but that friction force we don't know if it's a slipping or it is rolling. Okay, now applying the free body diagram needs also a kinetic diagram. Typically, the kinetic diagram is chosen along the assumed direction of the inertias. There are two inertias here, rotational inertia, which in this example we assume a counterclockwise to be a positive, alpha, and a positive acceleration or deceleration of the center of gravity G to the right in the x direction. And also we have in the y direction AGY, but it's a zero, we know by default. Alright, now equation of motion. First we apply the summation of forces for this entire rigid body to be equal to the mass multiplied by the acceleration along the x direction. Since this is a positive MAG, so it says positive, equal to P positive minus F. Second, the summation of forces in Y is N minus mg and equal MAGY. AGY is 0, so the entire thing is 0. The last equation is the moment. Now, the moment could be applied anywhere. We choose here to apply the equation of motion of the moments about G. So we calculate the moments of all the forces about G and then that's going to be equal to the moment of inertia IG multiplied by the acceleration. Now where this is the positive direction, counterclockwise. Alright, so first of all, the moment of G and P is 0 because the distance is 0 from here. And then the moment of the N is 0 because its distance is 0 to the normal direction is 0, so this extent. But however, the moment of the force F is not 0, and that's equal to F R, which is distance from here to here, cross F, or in scalar form is distance radius R multiplied by F, and it is positive because it's counterclockwise. So use your right hand rule. And notice that when this F is causing this wheel to rotate about G counterclockwise. So that's what we get here. Now the number of unknowns are the force, frictional force, we don't know it because we cannot simply assume it's a dynamic friction as a result of slipping where MUK, MG. We cannot say it is a static µs mg, or it could be a general F less than µs multiplied by mg. So that's why we keep it as is, and we have to make an assumption and verify. Okay, now we have F unknown, AG is unknown, we have the normal force is unknown, and the alpha is unknown. So 4 unknown with 3 equations. So we must need another equation. So that comes from a more in-depth analysis where we examine a case and verify. At that case, we have to make an assumption and see if that assumption is correct. If not, then we move to the second case. So what does that mean? It's similar to what we studied in the past static class, where we looking at a system friction force and examining whether that system, such as a box, is a tipping or a sliding. I think you remember that from the textbook. Going back to this problem, there is 2 conditions, slipping or no slipping. If we assume no slipping, meaning that at contact there is no relative motion between the ground and a point at the bottom of that wheel, and the only motion is that this is rolling, no skidding or sliding, then this becomes an instantaneous center of velocity, where we knew that from the kinematic analysis that the acceleration of the point G, the linear acceleration, or due to the translation, is equal to R cross alpha, or R alpha, right? And causing that to move to the right. So make sure that when you decide on the direction of AG and alpha, they must make sense. You cannot say that the counterclockwise rotation will cause this to go to the left. We know from the rotation of this wheel, this will go AG to the right. So make sure that, because we are dealing with scalar form, then you must use your common sense more. If you're using vector, then it's leave it to the math. Okay. Now we have introduced a new equation, which is AG equal to alpha R. And that is based on assumption no slipping. We will be able to calculate these four unknowns using three equations along with that equation. So we will be able to calculate this F over here from these four equations. Now this F is indeed there's no friction, or sorry, no slipping. If it's indeed there's no slipping, then the magnitude of that friction that we calculated based on this assumption must be less than static friction, μSN, equal or less. Otherwise, it's going to be slipping. And when it slips, then we have another type of equation where this force is going to be equal to mu Kn. So instead of using that, we'll be able to use this one if it's a slipping. Okay? So it's anyway. So you always could or should start with no slipping assumption and use that equation. If it does slip, but after verifying your F magnitude with the friction force, static friction force, if this doesn't work, then definitely it's going to be slipping. And with that assumption, you ignore this, and for slipping, you use this equation, which is, we know it. Slipping means dynamic friction is UKN. And in this case, this is not true. To lump sum all what we discussed in procedures and to help you solve any kind of dynamical problem, there are a list of 7 steps that summarize. So first of all, any problem you get, sketch it, draw the inertial coordinate system, and free body diagram, and the kinetic diagram. Specify the direction and the sense of the acceleration of the mass center, AG, as well as the angular acceleration of the body. It has to be compliant to each other. Also compute the moment of inertia, if needed, IG. Now, as we mentioned, IG, there's a lookup table you can use. Mostly, IG is described by the radius of gyration. And remember, IG is equal to kg r squared, where k is the radius of gyration constant. Then, if needed, you can apply the moment equation about different point, but we have to be careful that you calculate the moment of all forces, the moment about that point, to be equal to the inertias of the moments of the inertias, which is the Ig alpha plus mgy multiplied by the distance, and as well as that, or you can say r cross mag. For problems that involve rolling and slipping or no slipping, such as what we discussed, assume slipping, and then you use Ag equal alpha r, and if not, then use F equal to mu k multiplied by n. Alright, let's take an example and study this one in particular, where a spool has a mass of 200 kilogram. It does have a radius of gyration of 0.3. Sorry, I must correct myself when I was discussing about the radius of gyration for moment of inertia. Ig is equal to k squared multiplied by n. K squared multiplied by n. So over here we have kg is given, so by 0.3. The coefficient of kinetic friction between the spool and the ground is mu k equal to 0.1. Okay. Find the angular acceleration of the alpha of the spool and the tension in the cable. Alright. Now what do we have over here is this spool is being held by this cable. A moment is applied for 450 Newton meter, and it's counterclockwise because this spool, it might slip or it might roll. In either cases, this point IC or this point at contact, it doesn't move because of the cable. So this remains constant. So therefore, we already have one unknown, which is that the acceleration AG is going to be equal to R multiplied by omega, because simply this point is not moving, right? From this illustration you can make that. So that's one equation. Now, and because of that, so it will slip anyway. It will slip as a result of that torque. And therefore, the friction force, F, is going to be equal to the normal force multiplied by mu k. Okay, so procedures. So what we have here, we have a free body diagram, where the tension at point A is unknown, the normal force NB is unknown, the friction force, we assume it here to going to the left, and equal to mu k NB, where mu k is 0.1. And this is all equal to, of course there is a mg, equal to the inertia, where we assume counterclockwise Ig alpha is a positive, and we assume that positive mag to the right. First of all, this spool is not moving upward and y, so it does not have any acceleration. So summation of forces in y is equal to 0 and equal to NB minus mg, which is 1962. So we will know NB. We note that this point at contact is remain not moving, therefore we know the acceleration of that point, because this becomes a center of instantaneous velocity, which will help us calculate the acceleration AG, which is equal to 0.4 alpha. Now, apply the summation of forces in X, where to the right MAG is positive, so MAG equal to T minus 0.1 NB. Okay, so this is another equation here. Another equation for the moment is using the moment about G. Counterclockwise is a positive, so Ig alpha, where Ig is mass multiplied by the radius of gyration squared, 20.3 squared multiplied by alpha, equal to the moment of these forces. So the moment of the NB is 0, the moment of the external moment 450, which is a positive, so 450, minus the moment of the, or plus the moment of this torque T, and that's tend to rotate the spool in the opposite direction, right? So T multiplied by the radius, 0.4, that's the moment, armed by the force, and the moment of this force, which is also tends to make this, according to this assumption, to rotate clockwise. So it's negative 0.1 NB multiplied by the distance from here to here, which is 0.6. Okay. Let's give us another equation. So we have two equations with two unknown, alpha and t. Solve them, we get alpha is 7.5 radian per second square, and tension is equal to 797. So try this at home. See if you can get the calculations right. Let's take these two concept quizzes, and then we'll move another example. An 80 kilogram spool whose radius of gyration kg equal 0.3 kg is computed at g. We could have radius of gyration at different location, but since this is given at this g, so it's make sure that you know what does that mean. So this is on a rough surface, and there is a cable that exerts 30 Newton load to the right. The friction force at A acts to, and the acceleration of point G should be directed to what? Now, because this is an offset, this force from the G, this will cause this spool to rotate counterclockwise. So therefore, we know AG is going to go to the right, best way. Okay? Having a friction force in a rolling scenario like this one, and without slipping, it means that the force, that friction force, is in the direction of the motion. Unless it slips, then it's going to be opposite. Since the surface is rough and no assumption is made, or let's say no information is made about how much is that static friction, and it's rolling, then therefore this has to be the right. So both of them, the friction force and the acceleration, is to the right. Let's take a look at the same problem, but we want to calculate the moment equation about G. Now consider that a positive direction of moment is counterclockwise, right? Since this is a clockwise, so alpha Ig, which is negative alpha multiplied by Ig, is equal to the moments of the 30 and the moment of that force which is to the right. The moment of the 30 is also clockwise, because this tends to rotate the same as clockwise, so it's 30 multiplied by 0.2 negative. However, the moment of the force which is to the right but it's in the bottom side, is tend to rotate this counterclockwise, right? So it's going to be 0.75 multiplied by F minus 30 multiplied by 0.2 equal to negative alpha Ig. So the answer is A. Let's take this final group problem solving. I'll try to explain it without going into details, and I'll leave that to you to practice at home. This is a 500 kilogram culvert that has a radius of 0.5. Assume that the culvert does not slip on the truck bed, but it can roll. And assume that the thickness of this culvert is ignored. That means that we can calculate the moment of this shell cylinder using the formula of Ig of this equal to the mass multiplied by the radius, 0.5 square, because that's by definition the radius of gyration definition. Okay, so that's what it means. Now, what we want to find is the culvert angular acceleration when the truck has an acceleration of 3 meters per second square. So this truck is moving to the right. This is not slipping, it's just rolling. There's a contact point between the bed of the truck, which a point just at that contact has a tangential component of 3 meters per second square, right? And it might have that point a normal component, which is going to be equal omega square r if this is rotating, right? If there is omega. So the method for solving this problem will involve a couple of things. First, drawing the free body diagram, labeling the forces, examining this point A, and then apply the kinematic equation, right, with a non-contact of 3 meters per second, so that we can relate AG, because the three equations that we'll obtain will have 4 unknown, and we need to calculate these. We need another equation which comes from kinetic, which links it to the 3 meters per second square. Now we don't have to put all the equations. Since we're only looking at the angular acceleration, we're going to focus on that. Alright, so the moment of inertia for this culvert about G is simply mr squared. And that's going to give us 125 kilogram meter square. Draw the free body diagram. So it's rolling without. So if we assume this culvert to move to the right, as a result of this culvert to rotate counterclockwise, then, and there's no slipping, then the force is in the direction of the movement, the friction force for the rolling. Okay, so we have a reaction force M, a force F to the right, a mass or a weight. We assume Cartesian coordinate system to the right is positive and y positive to the upward, and counterclockwise is positive. Kinetic equation labels the inertia due to translation and inertia due to the rotation, and in their positive manner. Write the equation of motion. Now you choose any point. If you start with let's see what is the best way to start. Now I'm looking at a relation between alpha and AG because I'm not interested in N. or in the force calculation. So if I calculate the moment about G, then the F force will appear and will be out in any way. If I calculate the summation of forces about Y, I mean immediately we know that N is going to be equal to 500 multiplied by 9.81, so there's no need to do that. If I calculate the moment about point A, then I will ignore F and N because their moment is 0 and the moment of the weight will be gone. So the only thing will appear is that the summation of all moment is going to be equal to 0 and equal to the moment of the inertia of that 500 AG plus 125 alpha. So the moment here is going to be 125 alpha because it's positive. The moment of this inertia seems to be causing, because we're calculating this about A, so that 500 AG R cross F or 500 AG gonna cause this to rotate clockwise, so it's a negative. That's why we have a negative here. Okay. So they have one equation, two unknown. We need another equation which will be obtained from the kinematics. Kinematics is the analysis of the motion. Now we know at contact that this contact is the same as the bed contact of the truck. So it does have a tangential component equal to 3 meters per second, which is AA, 3 meters per second. And that is equal to going to be equal to the tangential component. Let's put this together in a relative motion analysis of the acceleration that we learned. So AG, the acceleration of the G, is equal to, as a vector, this is the right, and the absolute acceleration of A at A plus alpha cross RG relative to A, so that vector, minus omega square RG relative to A. This is the relative, if you remember, this is the relative acceleration. Great. So alpha, we know it. It's an unknown, but it's alpha k, and this is a positive. Omega, also assume it to be positive. And R G relative to A is this vector going from A to G, so it is 0.5 J, the cross product, and same as here. So yeah, simplify that. We know from the unit circle of the cross product, you distribute the cross product and then you reassemble all of the components of i's together and all components of j's together. So you're going to end up with that. You try this again at home. So this is AGI equal to that. So W is going to be equal to 0 because there's nothing in the left side hand of J's component. So mean this is, at this moment, is not rotating. It does experience acceleration because the 3 minus 0.5 alpha is going to be equal to AG. That's going to give us another equation. So AG that we know if solved together with the first equation, going to provide us the solution of alpha and AG. Just wanted to reemphasize that the acceleration of point A here is purely due to tangential here. Okay? AN or AAT. So solve these two equations, you get the alpha equal 3 radian per second, and AG equal 1.5 meter per second. Both of them positive, so our assumption is correct. So with this example, I conclude chapter 17. I think the key for understanding this chapter is to solve and solve more problem. All right, so good luck in this chapter, and thank you for your watching this video.